Hey everybody, welcome to the video. I am filming inside of a building because it's pretty cold outside. I wish the sun were just a little bit bigger today so it could be a little hotter. Thinking of that, how big is the sun? Or what is the mass of the sun? I mean, how do we even measure that? If we could travel the giant distance to measure the mass of a giant sun, we would die because it's hot. I want to explain the process of measuring this big thing as simply as possible. The answer to this question can be found like this. Hey Siri, what is the mass of the sun?
The solar mass is a standard unit of mass in astronomy, equal to approximately 2x 1030 kg.
That is all. And as always, thanks for watching. Okay, but somehow we can figure it out, otherwise Siri wouldn't know. First, let's talk about the law of universal gravitation. Well, that was developed by Isaac Newton, and it's like a formula or an equation that looks like this. What the heck? How did he get that? I mean, where did he come up with that? Well, he did a bunch of experiments and observations and whatnot to figure out this equation. But that's outside of the scope of this video. If you'd like to learn more, you should research it. It's pretty interesting. Another thing that we need to know about is big G. It's part of that formula. That is the gravitational constant, which we now know is 6.67 times 10 to the negative 11, and then a bunch of weird units like this. I would highly encourage you to research this on your own as well. It's fascinating how this number was found. Big G is a key part of the law of universal gravitation. Okay, awesome. Ultimately, we will need to find the mass of the sun with this law. But first, we need to find the mass of the Earth using the same law. To find the mass of the Earth, we need a lens cap. If you drop something, it falls to the ground at a speed of 9.8 meters per second per second. That means that there's a force of gravity acting on it that's accelerating it down towards the ground. We know this value by dropping things and then measuring how fast they speed up. F is equal to ma, which is Newton's first law, is used to find that force that's pulling the thing towards the Earth, or the force of gravity due to the Earth. From the law of universal gravitation equation, we know F, the mass of the object that we're dropping, and we know that we're looking for the mass of the Earth. So all that's left is to find R. Well, if a thing is sitting on the surface of the Earth, it's still under that force of gravity, and the distance in between that object and the center of the Earth is the radius of the Earth. But how do we measure the radius of the Earth? You dig a hole to China and then divide by 2. And as always, thanks for watching. Actually, all you really need is the circumference. Long ago, ancient Greeks noticed that there was a certain year that the sun would shine directly into a well in a certain town. So all shadows just point straight down, because the sun is straight up. In another town on the same exact day, shadows were not straight down. They were angled at a little bit of about 7.2 degrees, because the Earth is round. They knew that the distance in between the towns was whatever the distance was, so they could say, well, if this distance causes the shadow angle to change by about 7.2 degrees, which they measured, what is the distance of 360 degrees? Or the circumference. The circumference can be found with pretty simple math. And then from there, you just need to use some basic geometry to find the radius of the Earth. Well, with all that done, the Earth's mass can be found. Hooray! Now, we can use the same law to find the mass of the sun. There are only 2 things that we need to know from here. F and the distance from Earth to the sun. F is the force of attraction between the Earth and the sun. And coincidentally, well, not really, but that force must be equal to the centripetal force, which is a force that keeps things moving in a circle. The force, let's just say that there's this we can find the centripetal force of an object using the formula F is equal to mass times the velocity squared divided by R. And, well, we already know the mass of Earth, and we also know the amount of time that it takes to go around the sun, which is about 1 year. We use that to find the speed. But the only missing piece is the distance of the sun. If we can find the distance to the sun, then we can figure out, first of all, R, And then second of all, the speed, because we know how long it takes to go however far that distance is. We can measure the distance to the sun in a few different ways, but a classic way is using a technique called parallax. This technique was used all the way back in the 1670s. I would recommend researching this on your own because it's really interesting. Simply put, parallax measurements can be taken by you right now. What I want you to do is stick out your thumb. And now, thumbs up this video. Hold your thumb an arm's length away from you and close one eye. And then close that eye and open the other one and then do this back and forth. You'll notice that your thumb kind of bounces around and shifts relative to its backgrounds. Well, that's awesome. When astronomers measure the parallax of an object, they have to know the distance of separation between the 2 points it was observed from. In this case, it would be your eyes. And so what they do is they'll measure it from like one point in the year, and then as the Earth rotates halfway around the sun or whatever, then there's the second measurement. And so they have a separation of a lot of millions of miles. There you go. You can use some kind of complicated math to reveal great distances to planets or stars using this parallax technique. There are a lot of pieces to keep up with here, but putting it all together, we can find the speed of the Earth as it goes around the sun and then use that to find the centripetal acceleration. The speed can be found by using the radius of the Earth's orbit to find the distance it covers in about 1 year, and then set that centripetal force equal to the law of universal gravitation formula, and boom. With some algebra, we can figure out what the mass of the sun is. It's pretty big, about 1.989 times 10 to the 30th kilograms. And as always, thanks for watching.